Okay, so now I want to show everybody that solving a system of equations, you can really use three different methods. We have graphing, we have the substitution method, and the elimination method. And the method that you choose is sometimes kind of an art form. You have to sort of figure out what's going to be the easiest way to do this. So if I look at number one, I know that I could substitute because I have these y's that are by themselves. So I could set these things equal to each other, and I could solve for x. It wouldn't be that bad. But I have these fractions, and I'd have to find a common denominator. And so maybe I don't feel like doing that. But luckily, the teacher gave me this nice looking graph here. So I think that this is a case where the lines are really easy to graph and solving would be kind of problematic. This is when I think graphing is the easiest way to do things. So I'm going to really quickly graph this. I'm going to start at 7, and then the slope is negative 1, 6. So I go down 1, and I go over 6, and I'll do that again. And I'll go down 1 and over 6. And then maybe I'll just add a point back here, because maybe it's back here, and I'll go up 1 and back 6. And there, I've got my points, and I'm just going to sort of clumsily connect them. There, just like that. And then maybe I'll graph this other, well, I'll definitely graph this other line on the same axes, and it starts at negative 4 and it goes up 3 and over 4 because the slope is 3/4. So see, I'm going up 3 and over 4 each time, and pretty quickly I'm able to figure out my common solution. It's this point right here. Again, I could have done the substitution method if I really wanted. I could even have done the elimination method if I had really wanted. But in my opinion, because I have these slopes that are fractions, finding a common denominator and solving, though possible, it seemed a lot easier to me to just graph it. And so the solution, by the way, it looks like it's at 12, 5. I should always write down the answer there. So this is, again, I would definitely solve this one by graphing. But if we turn our attention to the next one, number 2 here, I could graph this, especially the second one would be pretty easy to graph. It's already in slope-intercept form, but my 2x plus 5y equals 29, it's not going to be the prettiest thing to graph if I put it in slope-intercept form. I mean, the y-intercept, I can tell you, is going to be 29 over 5, and the slope is, well, the slope's not that bad. But I think that this one is a good candidate to use the substitution method, because if you've already got a variable that's isolated, it's not that bad. You can just take this thing that y is equal to, which is negative 3x minus 2, and just replace it in the other y, in the other equation. So solving this one, I think the substitution method is definitely the best way of doing it. Again, that's because at least one variable is already isolated for me. So I'm going to write my other equation, 2x plus 5, but instead of writing that y, I mean, I could write y, because I know that it equals 29. But remember, I could also, instead of writing that y, and I can substitute this other value that y is equal to, negative 3x minus 2. And now I can solve this system of equations, and I can do it pretty rapidly. So I know that I distribute the 5 through, I get negative 15x, negative 10, and here's a 2x. Okay, so now I'll combine like terms. 2x minus 15 is negative 13x, minus 10 equals 29. Just keep going the way we do. I have negative 13x equals 39. So when I divide by negative 13, I get x equals negative 3. Cool. I'm all done. Just joking. You're not done until you find both x and y every single time. I'll just do it in the same color. Then I know that it's not that hard to find y, though. Y equals negative 3 times x minus 2. Well, negative 3 times negative 3 is 9. And 9 minus 2 is 7. There. So now I have a solution. Negative 3, 7. Again, the reason I chose to use the substitution method on this particular system was that one variable was already isolated in my second equation. So now we can go look at our third case. Now in this case, both equations are already written in standard form. Neither equation really offers a really easy way to isolate a variable. So I'm going to use our third method called the elimination method. And this is where I can add these two equations together and make one of the variables just disappear. I can eliminate it from what I'm looking for, or from my situation, and then it's very easy to solve once that's done. So Let's just pretend I was going to add these together right now. If I added these equations together, 2 plus negative 3 is negative 1x, or negative x. And then 3 plus 2y is 5y. And then, of course, 9 plus 19 is 28. Okay, cool. I added them, except I didn't actually eliminate anything. So I got to back up. What I actually have to do is manipulate the equations so that when I add them together, one of the variables goes away. I need to have the same coefficient in front of one of these letters, except that I need one to be positive and one to be negative so that they cancel each other out. So I'm going to just nominate the letter x. I'm going to eliminate x. And I'm going to do that by, it's almost like finding a common denominator, actually, because I want the top x to be a positive something and the bottom x to be a negative something, but I want that something to be the same thing. And I'm thinking about 2, and I see a negative 3. So I have an idea. What if I just multiply the top by 3? If I do that, I'll get 6x, and then I'll get plus 9y. And here's a very common mistake. People think they're done because you multiplied the x and the y, but you have to multiply the entire equation. So I have to multiply the right side, and 9 times 3 is 27. So now that I have made this into a 6x, I can really easily make the other equation, which I'll do this in a different color, I can make that into a negative 6x, and all I'd have to do is multiply that equation by 2. Because 2 times negative 3 is negative 6x. 2 times 2y is 4y, and 2 times 19, I think, is 38. Look what happens when I add these equations together. I'll go this way. Well, 27 and 38 is 65. 9y and 4y is 13y, but then the really beautiful thing here is 6x plus negative 6x is not x. It's not 0x, it's just 0. Well, I mean, I guess it is 0x, but it's just 0. Okay, so it's gone. I've eliminated the letter x. And now solving for y is simple. I just divide both sides by 13. Y equals 5. So easy. I didn't have to convert any of these equations. And all the numbers that I've been working with are whole numbers. They're nice, easy to multiply numbers. So I'm totally done. Just kidding. You're not done until you find both letters. Now this is where the elimination method isn't quite as elegant, because now I have to find x, but it's not that bad. I'm going to take the y equals 5, and I'm going to choose one of these equations to use. I'm going to choose the top equation, because 9 is smaller than 19, and so I think it'll be easier. So I know that 2x plus 3 times y, which I now know is the number 5, equals 9. So 2x plus 15 equals 9. If I subtract 15... now I know that 2x equals negative 6. Divide by 2. X equals negative 3. Now I found my solution using the elimination method. All three methods will work on every single system of equations. But your goal as a mathematician is the art of figuring out the best way to solve the problem. And you can see that different problems have different best ways.